Hi everyone, I hope that you're all doing well. Welcome to the fifth lecture in the series on statistics for the social sciences, from basic descriptive statistics to inference on regression. And speaking of regression, today the topic of the lecture is that we are going to discuss relationships between two variables known as bivariate relationships. And we won't discuss regression immediately today, but we're going to discuss the important foundation of it, which is the tool of correlation. And specifically, we'll discuss Pearson's correlation coefficient today. First, however, we're going to discuss scatterplots. Those are pretty easy to understand, but I do want to point out how they can be understood at a higher level, since that kind of forms a graphical intuition for what correlation really does in a sense. We'll go over some practice interpreting correlation coefficients without really calling them that by just looking at scatterplots. And we'll discuss some caveats about scatterplots, so the problems of outliers or the use of highly discrete data, and we'll see kind of how that forms some characteristic problems that we'll want to think about as we go further in our analysis. And then what we'll talk about is correlation, which is a numeric measure that helps us quantify what's going on in a scatterplot. In other words, when we've got two quantitative variables that we're trying to put in relation to one another. We'll go over some key correlation facts, then I'll show you a little bit of the theory, so we'll do a derivation of the correlation coefficient. We'll go over some caveats, so some things you need to be careful about when you're using the sample correlation coefficient to summarize a set of data. And then we'll talk a little bit about an example where we do compute the correlation coefficient by hand. And then finally, although I didn't put it in these bullet points here, I do want to show you a bit of an alternate picture on the geometry of correlation, since it can be quite informative, I think. So let's go right ahead. So here's the executive summary of the lecture. Scatterplots show bivariate relationships for quantitative variables, and we typically put predictors, or the variable that we think is either causal or it's just one that we think makes sense to treat as the kind of fundamental variable, and we put the outcome, or the response, or the dependent variable, these all mean the same thing, on the y. Pretty straightforward. Scatterplots can suggest linear or nonlinear relationships of different directions and different strengths. So the direction of a scatterplot generally means what happens when you increase the value of your predictive variable. Does your response variable also increase, making it a positive relationship or indicating a positive relationship? Or does it decrease, indicating a negative relationship? Strength we can generally quantify by R, the sample correlation coefficient, but we can also just assess this visually by looking and seeing does there appear to be a clustering of points around sort of an imagined line, which we'll later learn to quantify using the regression slope, or is there more of a spread? We do need to be careful with outliers and highly discrete data. In other words, we need to be careful when we've got values of the variable on either variable that are, say, larger than 1.5 times the IQR plus Q3, or the same but for Q1 and with subtraction in there. We also need to be careful with highly discrete data, because scatterplots in general don't form a great tool for looking at highly discrete data, in part because the more discrete a variable is, generally speaking, the less informative those quantitative summary techniques are. One point I also wanted to mention too is that nonlinear relationships, although visually obvious in scatterplots, also are something we need to be careful about because they're not picked up well by the correlation coefficient. A correlation coefficient, on that note, summarizes linear relationships for quantitative variables. It can be understood in many different ways, and I'll show you a number of them. One is that it's the mean product of z-scores for both variables. So we basically turn each variable into a standardized version of itself. We take all of the pairs, so person i's score on variable x and variable y, multiply the scores together. We add up all those pairs, and then we take something that's roughly a mean. We do need to use the n-1 Bessel correction again, although it's not exactly the Bessel correction in that case, but it comes basically to a mean. So a couple of good properties about the correlation coefficient. It's units-free and bounded, so it varies between -1 and 1 inclusive only, meaning that it can be interpreted, generally speaking, as a kind of percent if you want to move the decimal over a couple of places. So for instance, a correlation of 0.65 could be understood in a certain way as being like 65%, although we'll talk later on about how to actually formalize that, but just saying it's bounded, so you have a natural scale. But again, the correlation coefficient does not pick up nonlinear relationships very well, so we want to be careful about that going forward. So let's go over some basic terminology for bivariate relationships. So far we've been focusing on univariate analysis, but we need to go ahead and now turn to the situation where we've got two variables. So if one variable explains variation in the other variable, we call the first the explanatory and the second the response variable. There's many other terms for this, but this is just the set that I happen to prefer. Explains variation is a phrase that has only a statistical meaning, so it doesn't have to mean that there's real causality. And in general, sussing out causality is pretty hard in social science, and so it might surprise you to learn that what we're not going to do in this class is prove anything ever or definitively show that something is true or false. Instead, what we're going to do is provide evidence in favor of or against certain kind of working hypotheses. So that's a couple of important points there. So one way to see that is that if X really causes Y, so let's say that we think that let's pick a simple example, the amount of time that you spend training to play a particular sport explains the number of games that you win, it seems pretty clear that that relationship goes one way. Maybe there's some claim for reverse causality, say maybe you win and thus you feel motivated and you train, but most of us would say that it's pretty intuitive that you need to train before you start winning. So there seems to be a kind of clear theoretical reason to prefer X causing Y, but it's still the case, however, that if you literally just transpose a scatter plot, you put games won on the X and time spent training on the Y, you're still going to see the same positive relationship actually. So what that means is that statistically, the relationship between X and Y is the relationship between Y and X. There's really no distinction. We'll see when we come to regression that there is a minor distinction between the order of the variables, which has to do with basically how we deal with the normalizing ratio of standard deviations. We'll come back to that. But for the most part, you can know that the math can't really tell us what the causal variable is and what the outcome variable is. That's something that we have to use social theory for. And I just kind of said this already. So let's talk about how scatterplots work. It's pretty straightforward, and I want to pull up the graph here. So they are things you've almost certainly seen before in your life, but if you haven't, no big deal. Here's an example of the relationship between height and leg length from data from the NHANES 2017 to 2018. And as always, my code is in the comments. You will need to construct an analytical extract from the NHANES data because they're set up in separate files on the CDC website. But you can see my comments for some suggestions on how to do that. If you're interested in this data, I'm more than happy to show you how I created this analytical extract. So what this shows us is in the first case here on the left-hand side, we've got leg length on the x-axis and standing height on the y-axis. And there's a relationship here that seems pretty obvious. But it's not really clear what the direction is, right? So we just see a statistical association. The association makes sense, but does leg length really cause standing height? Isn't in one sense standing height just a kind of addition to leg length in a sense? So leg length is just a component of standing height. So this is really in a sense almost like looking at a scatter plot between leg length and torso length, and then does one really cause the other? I think this is a situation where it's clear that it's kind of hard to say what's going on here in causal terms, even though there's a clear statistical association. Notice that you could still make the case, so you could look at the graph on the right, that maybe the order of the variables should be inverted, and we should think about standing height as a predictor. And I want you to notice that when you do transpose a scatter plot in that way, the basic pattern between the variables is preserved. You should try to convince yourself that that's true, even though it looks a little bit different. And what I want you to pay particular attention to is the position of the outliers, because those kind of show you this axis of symmetry over which the graph is flipped when we transpose a scatter plot. Scatter plots, by the way, happen in variable space. That probably sounds somewhat unclear. And when I explain what it means, it'll sound obvious, but you'll see that it has a point later on. So what it means to happen in variable space is it means that the scatter plot has on the axes different variables. So here leg length and standing height. There's another way of thinking about the geometry of correlation where the axes actually represent people. And that might seem a little strange because we typically have more than 2 or 3 people in a data set. So how can we have more than 2 or 3 axes? And the solution to that is that we'll use our imaginations and the standard tools of linear algebra. But we'll come back to that later on. That's not a big part of this discussion, although it is something that I want to mention. So the setup where we've got variables on the axes is just one way of doing things. You may want to note here that if you are looking for where do individuals appear in this way of visualizing things, individuals are particular points. So individuals in this case are defined by their score on two different variables. So the distinct points, although sometimes there's this overlapping phenomenon, but the distinct points, whether or not they're uniquely visible, are where the individuals show up. So let's practice describing some scatter plots. And again, you'll want to probably pause the video and make sure that you can follow along here. But I'm going to go ahead and make sure that I keep a good pace and just describe it immediately. So let's pull up that NHANES data, and let's now look at the relationship between arm and leg length. So what's the form here? Well, we would say that this looks like a fairly linear relationship. It's pretty clear that as arm length goes up, so does leg length, without a whole lot of breaks in the pattern, even though it's a little bit loose. It's a positive relationship since we've got an increase in one variable leading to, or predicting, to be most precise, an increase in the other, and the strength. So the strength appears to be reasonable. There's definitely a clear pattern here, but it's the case that there's some fuzziness and it's not a totally exact relationship. Here's another situation. So what's going on here? So the form in this case is curvilinear. And I say that because it's obvious from the graph that between about 10 and 30 centimeters of arm circumference, your arm length goes up pretty consistently. But as your arm circumference goes past a certain point, past about 30, your arm length then can take off, right? So there's kind of this really interesting situation there where there's a nonlinear relationship. So arm circumference, once it gets past about 30, is associated with an exponential increase in arm length. It still is a positive relationship, so there's no point at which having a larger arm circumference predicts that your arm length will go down. And the strength here, even though there's a clear curvilinear pattern, we want to be apprised of the fact that a correlation coefficient, for instance, our main tool for quantifying these relationships at this point, only picks up on the linear component of the relationship, and we'll see a little bit more detail later on. So we would say here that there's a strong curvilinear relationship. There's not an especially strong linear relationship, at least in subsections of the graph. So let's discuss some important caveats about scatter plots, and the first one of these is outliers. So you should watch out for outliers, just as you should generally in statistics. So what if we look at this graph here? This is a graph showing the relationship between hours worked and weekly pay. And you can see that as hours worked last week at all jobs increases, it appears that weekly income, generally speaking, goes up. But there's some clear outliers. So you might look at the person who reportedly worked 200 hours a week and yet appeared to make a fairly paltry weekly income. And then there's some other people too who are outliers and not as strange. They're at least working a lot and also earning a lot, but some of those are somewhat implausible. So people mentioning that they had 110, 120, 150, 40, somewhere in there, hours of work last week, which you probably know is pretty close to impossible. So even if you're thinking you work 10 hours a day, 7 days a week, that's still, only 70 hours a week. So we might look askance at these people saying, they were working something like, 100 hours, something like that, right? You'd have to be working more than 12 hours a day, 7 days a week, and actually substantially more than that. So how can we answer that question? Well, we can use our statistical measures of association, which will allow us to pretty quickly drop those people and rerun a summary statistic like the correlation coefficient. But we can also just remake the plot without the outliers, and that's what I do here. So in this case, the relationship does seem to dissipate, even though we dropped that one outlier who was kind of bucking the trend. We also dropped a lot of people who, in fact, more closely hewed to the apparent trend. And the correlation coefficient here between these two is actually cut in half. So we go from a sample correlation coefficient of 0.4 to one of 0.2, which is relatively low. And in a certain sense, that might make sense because it's typically not the case. Hours worked each week and weekly pay would really only have a strong linear relationship if there weren't much dispersion in incomes. But because there's quite a bit of dispersion in incomes, it means that you could work a lot and be paid relatively little per hour, or you could work a little and be paid relatively a lot per hour. And we know that there's a lot of variation in income and not a lot of variation in hours worked. So what that means is that that kind of noise in the income, if you like, or really just variation, it's not fake, it's really there, but that high variation in income that's generally speaking not super closely associated with this low variation in hours worked leads there to be not too much of a relationship. I also want to point out the problem of discrete data. And it might seem like we're flying through this, but scatter plots at their most basic are pretty straightforward, and we're going to want to spend more of our time on correlation. But you do want to be aware of discrete data. So with discrete data, your scatter plot can end up looking pretty dotty, like this one on the left, because scatter plots don't have a third dimension in the standard construction. So in this graph on the left, I actually used a plotting technique where you can kind of see, although it doesn't look very good, where we are stacking people on top of each other. So for example, at the point, say 10, at the point 12, the circles are a little bit thicker. And what that indicates is that there are more observations there, although it's a little bit hard to see. But again, we don't see a direct representation of it because when we draw the circles right on top of each other, in some plotting routines in Stata, that actually there's no additional coloring or filling there, meaning that it's totally impossible to tell where there are more observations that happen to share the same coordinate, whereas or as opposed to a situation where there's only one point for a given coordinate or a set of coordinates. So there's a simple solution to this, and then there's a harder solution that's kind of interesting. The simple solution is given on the right. We produce random noise here, and we make the random noise louder when there are more observations. So when I say random noise, I mean that there's some blurring in this direction, that direction, basically in a circular fashion. This is sometimes called spherical noise, kind of scattered around the high-density points. But it's generally speaking a function of how close the noise is, like the amount of noise is a function of how close it is to a kind of bunch of data that would be seen if we had a third dimension here. In Stata, you can do this with the syntax scatter y x and then jitter and then a percent. So Stata in this case does have a requirement about the order of variables, which is not always the case. We'll see that it's not true with correlation. But when a scatter plot arises, what you need to do is put the y variable first and then the x variable second. So you don't literally need to write scatter yx, but what you instead want to write is scatter y variable x variable, comma jitter, that introduces the jitter option, and then you can put in a percent there. So I'll show another approach here. You could also fix these with a contour plot, and you could get this code on the right with the command kdense2yx, and you'll need to install it. So you can write ssc install and then whatever command that you heard about. So in this case, you could just write ssc install kdense2, and it'll install it free of charge. It's a user-written command. But how do we interpret this cool graph? So this hopefully looks to you like a graph that you might have seen on a topological map that shows you basically the height of mountains. And what's going on here is that when you see these contours, in other words, these curvy lines, what these basically represent is the height at a fixed point. So what this means is that if we travel along one of these curves here, we would not change height, right? It's a level curve or a level set, as it's sometimes called in calculus. And what that means is that the height of the function at a given level curve is all the same if we could have a third dimension showing the joint density of the two variables. And when we've got circles that are concentric or shapes that are concentric, meaning they're contained within other shapes, that's meant to indicate a higher peak. So you can see here that the highest peaks are predictably at 16, and 12. And what all those concentric circles, and they do get kind of circular in the end, are telling us is that if you traveled along that circular path in the xy plane, you would be stuck at a fixed height in the third dimension, sometimes called the z dimension. And so what that means is that where you've got more of these concentric circles, you've got, if you picture a three-dimensional density plot, of which I'll show an example in a moment, you would have higher peaks there. So this is a cool way to visualize this, and I recommend trying it out. We can also go ahead and look at a couple of other more complicated things here. Oh, I apologize. I actually showed that joint density plot in a past lecture. You can go see that. That's actually a couple of lectures ago, but if you want to see what that looks like, go back and check that out. What this is showing here is just a way to represent that with 2 dimensions. So I did want to show this kind of one advanced scatterplot technique, actually. Our book, again, for people that aren't in the class, that's Moore, Knotts, and Fligner, The Basic Practice of Statistics, 8th edition. They show us a way that we can do some kind of crude trivariate, or we'll just say multivariate generally, analysis using scatterplots. So you can see in this case, I plotted the relationship between father's education and respondent's education, but I showed the relationship for men and women separately. You'll note that there's a couple of things here. One, we haven't learned how to make lines of best fit yet. We will learn that soon enough, but I don't want you to worry about that too much for now. That comes from a technique called regression analysis that we'll learn soon enough after we learn correlation. You'll notice here that the lines look relatively similar. They're actually not statistically significantly different, but they do look a little bit different. And what that tells us is that there's a couple of different variables here. So controlling for a person's gender, it appears that there is some preliminary evidence there's a difference between the relationship between the father's education and the person's education, depending on the person's gender. We do run into the problem of dimensionality shortly after this. It's hard to picture R4, and R4, by the way, just refers to the 4th dimension and further beyond that. But there are some ways around this problem, and I'll discuss the general approach that we can take later on. So let's move to the numeric measure of association associated with scatterplots, or at least one of them, which is correlation. So what are some of the most important things to know about correlation? Well, first of all, correlation measures the linear relationship between 2 variables, and it's got a kind of number of important properties. So one of them is that correlation is not sensitive to the order of the variables, as mentioned before. So you can think about it as capturing the same sort of thing numerically, whether or not you have one variable on the x and another variable on the y, which won't be true of regression. So correlation can't say which variable is causal, and it doesn't even require us to decide on a causal or a predictor variable. Notably, correlation is also not sensitive to units of measurement, so you can add constants to each variable and the relationship won't change, and you can actually multiply each variable by a constant. R mostly won't change, and by the way, again, R is Pearson's sample correlation coefficient, so at most the sign will flip if you multiply by a negative number. The sign of association matters a lot. So what that tells us is that when it's positive, that means that when one variable increases, so does the other. And this would just be represented by a correlation coefficient greater than 0. And if it's negative, that means that when one variable increases, and again, which one is y and which one is x doesn't matter, the correlation coefficient is less than 0. So it's a little bit like a slope, although again, it's not exactly a slope. The regression slope is what we'll literally say is a slope. And again, correlation varies between -1 and 1 inclusive, so you can think about it as being kind of like a percent association. Now, there's some key caveats that I want to mention about correlation. First of all, you shouldn't use correlation on categorical data. And the reason for that is that it really obviously doesn't make sense for nominal data, because the mean and thus deviation of an observation, which you hopefully have done the reading and know that deviations, again, and means play a role in correlation, so that makes no sense. But even for ordinal data, it's not especially meaningful. The reason for that is that the deviations of individuals are not directly comparable because units are not necessarily of the same size, even if they've had numbers assigned. So don't use correlation, generally speaking, on ordinal data. It's not really going to give you very much useful information. Correlation, again, only captures the linear part of curvilinear relationships, so it does not tell us if 2 variables have, say, a perfectly parabolic relationship, that there's really anything going on there. In fact, it'll have, if you have a truly exactly parabolic relationship, correlation ends up being 0. So it only captures linear relationships. It's not resistant to outliers, so if you have high weight observations that are also totally breaking a certain underlying pattern, those can show a correlation even where there's really not one in practice once you drop those. And the reason for that is that, as we'll see in a moment, the correlation coefficient works by measuring the co-deviation of observations on 2 variables from each variable's mean, respectively. So it's really sensitive to high deviations from the mean. And then finally, correlation, like all single number variables, that should actually say measures, is pretty limited. So in this part of the lecture in class, I go to Top Hat and ask people to guess the correlations of these randomly generated variables. And you might take a look at this and take a best guess. I would say that for the correlation between A and B, that looks pretty strong. I would guess between 0.8 and 0.9. Again, just using my facts that it's positive, it's bounded between -1 and 1, so that means it's bounded between 0 and 1, and it looks strong, so I would guess it's closer to 1 than 0. For the correlation between A and C and B and C, I would guess that those are both probably a little bit less strong, maybe somewhere in the realm of like 0.6. The correlation between A and D appears to be total noise, and actually the same is true of B, C, and B and D and C and D. So let's take a look. And this is a correlation matrix. So you can see that it's got the same inputs on the on the rows and on the columns. And what that tells us is that to find the correlation between two of the variables, we need to look inside the matrix and then look, say, at a particular cell. So first you'll note that the correlation between a variable and itself is always equal to 1, intuitively enough. And so that's what's on the main diagonal there. But if we look at the correlation between A and B, we can see that it's above 90 as predicted. And then the others kind of more or less fall in line as well. So A and C, A and B, I guessed a little bit high. I said 0.65, but it turns out that those are closer to 0.5. And then indeed, it looks like the relationship between A and D, B and D, and C and D, those are all individually pretty close to 0. And in fact, the direction is almost hard to infer there because it is so small. By the way, people often wonder, why is this only a lower triangular matrix as it's formally known? The reason is that it's totally symmetric. So the correlation between A and B is the correlation between B and A, and thus most statistical software won't bother printing the upper half of this matrix. You could if you want, but it's not standard and you have to go out of your way. So that's the reason for that. Here's a couple of tricks. So let's again try to figure out the relationship between these variables here. So between P and Q, we saw before a relationship very much like that one. We would guess that that probably has a correlation of 0. The relationship between Q and R also, although it might appear to be a little bit more compact, like it's circumscribed between, say, a particular radius or rather a circular figure in the plane, some kind of contour. That still doesn't mean that there's any kind of linear relationship here, and in fact, it is just a cloud. The same is true of QS and QS and RS. Even though it appears that there might be a relationship in some respects, because again, there's not data evenly spread throughout the figure, notice that you can't necessarily predict the Y value from changes in the X value. So that's just a red herring. And the hardest one of these is the relationship between P and S. Note that that is a very small correlation coefficient because, as we'll see in a little bit, when you actually think about the correlation formula, because it works by taking these product of deviations from means, if you've got a lot of deviations from the X that are positive, and then you have a lot of positive Y deviations, then you have a lot of deviations from the X that are negative, and then you have a lot of positive Y deviations. Those will tend to cancel each other out. So we can again look at the correlation matrix here, and we'll see that all of these are very close to 0, which is kind of what we would expect once we get a better handle on this. So let's try to motivate the definition for the correlation coefficient now that we have some sense of what it means. So let's think about maybe the simplest sort of measure. What if we had a scatter plot and we decided to find the measure of association by, let's say, taking all the X coordinates and all the Y coordinates and multiplying together the coordinate pairs, and then sum them up and then take something that's like a mean, and maybe that'll give us some kind of sort of rough sense of the association. This is known formally in linear algebra as taking a dot product and then just taking the mean of the dot product. Again, remember that it's n minus 1, not n, but comes to basically the same thing. So that's kind of a nice idea. It gets us on the right track. And the answer that gives us here is 24.44. So you can see this represented visually here. What we're doing is we are, say, taking individual 1, x is 0, y is 1, so that gives us 0. Individual 2, the same is true. Individual 3, x is 2, y is 1, so we would get 2, and then so on and so forth. And you can see here, you may want to try that on your own to make sure you can get this. But when we try that, we get 2 plus 6 plus 4 plus 6 plus 25 plus 49 plus 56 plus 72. And then when we take the mean of all those things, we get 24.44. So that's kind of a cool idea. Here's the problem, though. So this measure will give us a different answer if we add an arbitrary constant to each variable. And here I show that on this figure. So if we look at this here, we see we've got these green dots and these red dots. Now the problem here is that the green dot represents adding an arbitrary constant to our x value. And you can probably work out the pattern here. We just add the value 2, and then we also add the value 1 to y. So the pattern is still visually pretty obviously the same if you just focus on the red or just the green. But that same simple measure from before gives 39.11. So it's not a good measure because all we did was, maybe this is a data entry error, and we realized that all subjects in a study stood on a scale that actually had not a correct balance. So we need to add something to both of their scores. In theory, if we're adding that same constant to everyone, it really shouldn't change the basic pattern of relationship. But it turns out to be the case that the mean dot product, as we'll call it, doesn't capture that well. So what if we first took the deviations from x and y, and then we take the mean? And so I can show you what that looks like here. If we first take the deviations from the mean of x and y respectively and divide by n minus 1, after we, I should make that a little bit clearer. If we first take the deviations from the means, and then we take the mean deviation by summing up all the co-deviation products, and then dividing by n minus 1, we're actually going to get the same exact answer as if we don't do that. So that's a really good sign, right? So if we have these two different variables that represent having an arbitrary constant added, that change our original variables, if we use this measure here, the covariance, on the original data set and then the second data set, we're going to get the same answer. So what if we did take that deviation of each variable from its mean first before trying our same basic measure of taking the product of all the coordinates and then finding the mean product of the coordinates? So what we would do here is we first take the deviations of the mean from x and y, and then we divide by n minus 1. And what that does here is it gives us the same exact answer whether or not we have this arbitrary constant added. And we can see that visually here. So let's look at this new set of data points. And these show us a pattern that's fundamentally the same to the last couple of slides. But notice that the data themselves are new, but they agree. So we have our original data, and then we have our arbitrary constants data. And then what we did was take the deviations from the mean. And these result in a third data set, which is, however, the same data set for each variable, or each set of variables, pardon me. So that's pretty cool. And when we go ahead and do that same procedure, we write down that measure as the covariance. So the covariance is the deviation from the mean on x times the deviation on the mean on y for every individual. And then we sum up all those products, and then we divide by n minus 1. Or in linear algebraic terms, what we're doing here is we're taking the dot product between two centered vectors and then taking the mean. Let's show why that works, actually, in some detail here. So let's write out the formula for the covariance. And what I want to first show you is the fact that the mean is basically scales linearly when you have constants added to it. So what am I talking about? If we have a new variable here that we call x plus a, and it's the old variable x just plus some constant a, and we try to find the mean of that variable, we can express that like this. So we have xi plus a here over n, and here we don't need to take n minus 1. And by the rules of the summation operator, adding up xi plus a plus xi plus a plus xi plus a just reduces to basically doing this. So x1 plus a plus x2 plus a, etc., xn plus a over n. In other words, we're allowed to pass through the summation operator. So what that results in then is this, and you don't have to know that specific rule, although it's pretty intuitive. You can just say, okay, we'll have all the sums of the x's, or the sum of the x's, so we'll just have I equal to 1 here, n xi, and then we have the sum over a, and there's no subscript, so remember our rule that we just write n times a. Another way to think about it is that if we counted up all these a's here, we would have n of them. So we have xi plus na over n. And then we can just break that up into two separate things here. So we have the sum of xi over n, which equals the mean, plus na over n, which just equals a. And so what we have here at the end is we have x bar plus a. In other words, the mean of some new variable x plus a, or x plus a bar, is equal to x bar plus a. So how does that help us out? Well, let's go ahead and just remove our work here because we want to keep the covariance formula in plain sight. So we'll cut that. So now what that tells us is that we can go ahead and come down here and rewrite the covariance of x plus a and y as follows. I'm not going to write out the entire index on the subscripts or the summation notation here. So we would have xi plus a minus x bar. And then remember, if we're adding this constant a to every observation, that means that the new mean is just x bar plus a, yi minus y bar. And actually the denominator here doesn't really matter. I'll write it in, but notice that it's not going to change the answer. So what happens here is we actually just see that if we distribute this negative sign here and here, we're going to have these two things. So this is a positive a and this is a negative a. These cancel out. And what we're left with at the end is just our original formula. So I'll just write that out one more time, even though it's somewhat tedious. So those two things cancel. And we just have our old covariance back. So the covariance is resistant to additive changes to one of the variables. But the covariance has a parallel limitation. It's not resistant to multiplicative changes to the variable. So what that means is that while the covariance of a plus x and b plus y is the covariance of x and y, the covariance of ax and by is actually equal to ab times the covariance of x and y. And what that leads us to is a better formula, although I'll again show the problem there. So here we see the same basic relationship between two sets of variables, but note that one of the sets of variables has a significantly larger kind of spread to it, and that's the variables represented in the red there, which is the original data. And then in our other situation with the green data, where we multiply x by 1/2 and y by 1.5, that seems to really compress the relationship, even though it seems obvious that in relative terms, the pattern between the points hasn't changed. So let's go back and show what happens when we multiply by that constant. So I hope you'll take it on faith that when you multiply every variable in a data set by a constant, that changes the mean by multiplying by that constant. I won't go ahead and prove that here since that's maybe a little more intuitive even. So what we would do here is write out what happens when that happens. So we'll just do this with one here. We don't need to do it with the other because the point is the same. And here I'm going to omit the subscript temporarily, so we'll just represent that with this. So how does this work? Well, we can actually factor out that a just like so. And again, we can write this out here. And then we can actually just factor this out one more time, because when we do this summation, so let's write out what this would look like. And I'll just represent the deviations with div, which is more convenient. So div x1, div y1 times a plus a times div xn div yn. And if we just go with the distributive property in reverse, this is simply equal to a times the deviation products summed. And we can write this back in now. So this is equal to a times the covariance of x and y. Okay. So how are we going to fix this particular problem, which is represented here by the fact that even though we have centered both of these variables, because I multiplied one pair of the variables by a constant, well, two constants, it actually went ahead and changed the pattern and it changed the numeric answer. So you can probably guess the next fix. What if we just divide out by the standard deviation of the variable first before taking the products and summing? So in other words, what we're going to do here is divide the entire thing by the standard deviation of x and the standard deviation of y, which reduces to dividing by their product. You can also think about this, however, as maybe meaning that we divide every single kind of co-deviation product by the standard deviation of each variable first, which is basically a product of z-scores. So let's show why that fixes things here. So let's say now that we're going to divide this figure by the standard deviation of x, right? And so how does the standard deviation of x scale with a change in the variable itself that is multiplicative? So we'll say this. So we'll say s of x plus a equals, now we need to remember our standard deviation formula, which is fortunately very similar to what we've been working with, because it's fundamentally very similar to the covariance. So we would say here axi minus ax bar, except it's squared because we don't have a second variable. This is a single number measure for a single variable. And bring this on top. Okay. And let me pull this a little bit bigger here just to make it clear that that's, whoops, let's do this here. Just to make it clear that the n-1 is inside of the radical sign. Okay. Sorry, my iPad's freezing a little bit here. There we go. Okay, so let's go ahead and now write this out. So we can, again, kind of, let's omit for the moment the square root sign, okay? So we're just going to actually make this the variance just to make it simple. And sorry, that's not a plus, that should be a multiplication here. Okay, so that means the sum of axi minus ax bar squared. And again, we can leave out n-1 since it's not important at this point. Okay, so let's go ahead and use our binomial expansion or foiling. So we're summing up then basically the following expression, axi squared minus 2a squared xi x bar plus a squared x bar squared, just like that, right? So you may want to double check for yourself that this follows all of the kind of conventional rules of regular arithmetic and algebra. Okay, so now what can we do here? Oh, and sorry, this should have a squared, so I should check myself. So what do you notice? Well, notice that there is an a squared in each term. So we can have an a squared here, and then we can just write out the inside. We've got xi squared minus 2xi x bar plus x bar squared. And then what you'll note is that this is just kind of a regular binomial expansion that we can simply write as xi minus x bar squared. And then we can put this back in, and that's the variance. And then there's implicitly a product here, or a multiplication operator. So then if we want the root of the thing, then we're going to say standard deviation of ax is equal to a squared, and I'm going to write this out like this for total clarity, and then we're just going to call this the variance of x here, right? And so then we can actually turn this into two separate products. So this is equal to a squared, and that has to do with the fact that exponents distribute when you're multiplying, times the root of the variance. And so this just becomes a times standard deviation. of x. So the conclusion is that the standard deviation of a times x is equal to a times the standard deviation of x. So what that means then is that if we think about this problem from before, that the covariance scales by a, so this is the bit that we don't like here. Notice now that if we take the covariance of, I'm going to keep the pencil changed here, ax y divided by standard deviation of a x here, this equals a times the covariance of xy over a times the standard deviation of x, right? And so then these things cancel out here, and we're just left with the standard deviation of x, which is a neat fact. So dividing by the standard deviation of this transformation then undoes the change. So then what you might think about is, why not just divide by the standard deviation generally? And what that causes to happen is that then there basically is no real length, or in other words, this ends up being a vector that's got unit length to begin with. So that's kind of an important fact. So the idea here is that by dividing out by the standard deviation, you can see that if we transform one of the variables x by multiplying by some arbitrary constant a, that if we then divide by the standard deviation of that new variable, it just returns basically the covariance of x and y divided by the standard deviation of x. So we might as well go ahead and divide by the standard deviation of x in the first place. So what that gives us is then the correlation coefficient. And sorry, I think I accidentally skipped a little bit ahead of here, so let's go back to that. Yeah. So we really want to hone in on this. So you can see here, first of all, this is a set of z-scores of these random two small data sets. And notice here that what's happening is that we've got these transformations of the sets of data. So we've got in red our original data, and then in green our original constants multiplied. But then what happens is that when we divide both data sets by the standard deviation of each of those, the pairs of standard deviations for each variable, so the original x and y and the transformed x and y, and then we also center them, what that means is that, although centering is not important in this case, we end up with fundamentally the same transformed sets of data. So then our original procedure, basically taking the dot product and then taking the mean, works, because it's going to give the same answer in each case. So how can we think about this? Well, again, it's either the covariance of x and y divided by the product of the standard deviations of the variables, or you can think about it as, if you want to move up the standard deviation of x and y out of the denominator, and so then just kind of leave them behind in the numerator. And there's proofs of equivalence in the back, by the way, in case you're not immediately convinced. Basically what ends up happening there is that you have the standard deviation of x. You can factor it so that it basically ends up being, you divide the individual deviations by the standard deviation of x, and the individual deviations on y by the standard deviation of y, and then you go ahead and multiply them and then add them all up and then divide by n minus 1. And what that means then is that the correlation basically ends up being the mean of all of the z products, as I'll term them. That's a term I haven't seen used elsewhere on the internet because there's not a standard term for it. But it's effectively the mean of all the z products. Or in other words, another way to think about it is that it's the dot product between the standardized variables turned into a mean. Again, the n minus 1 is effectively a mean, so I don't want you to worry about that, even though it might seem a little bit scary because it's not exactly n. And by the way, I do want to show that equivalence now, I think, since I do have a little more time here. So let's skip ahead. And you can see there's some formal proofs in the back that are nicer looking in case you do want to revisit these and take a look carefully. So let's see where I put this. Yeah, so right here. So you can notice, for instance, that we can get from that expression that I just showed you back to the original expression. The first step, we just write out the new way of writing the correlation formula. And then what we do, right, our next step is that we see that we're multiplying each of the centered variables and their product by 1 over the standard deviation of x times 1 over the standard deviation of y. Then we can factor that out, and it goes into the numerator, but then we can just rewrite that as 1 over the standard deviation of x times the standard deviation of y times this thing here on the right. I guess I can't really point with this Apple Pencil, but times the original covariance expression, and then that just reduces to the covariance expression divided by standard deviation of x times the standard deviation of y. There's another alternate expression that I want to show you, and actually it appears in the bulk of the notes up front, but this is a convenient time to show it. If you look at the second expression down here, alternate expression number 2, notice that if we actually go ahead and write the whole thing out, and it looks like a monstrosity, but it'll get simpler in a second, we've got the covariance of x and y over the standard deviation of x times the standard deviation of y. Notice then that we can actually factor out an n-1 in the denominator because when we multiply together, so first of all, you can turn the standard deviation of x, which is the root of the sum of squares over root n1, into the root of the sum of squares over the root n-1. And then you can do the same thing with y's standard deviation. You don't need to transform the tops, although sometimes you'll see that. But you'll notice that when you multiply root n1 times root n1, you just get n minus 1, I should say, back. What you get is an n-1 in the denominator, and then above that, in the numerator of the denominator, is the product of the sums of squares. And of course, there's an n-1 in the original covariance formula, and so those cancel out. And then what this becomes is simply the dot product of the centered vectors over basically the sum of squares for the variable x and the sum of squares for the variable y, only taking their root at the end, right? And so we'll see later on that that actually has a really nice counterpart in a totally different way of thinking about the geometry, but we'll come back to that soon enough. So that's how we get from one formula to the other. And I've kind of already shown this, but the 3 expressions that I want you to be aware of are these ones here. So the covariance is a separate idea. You should know what the covariance is. But then look at the correlation. So notice that it's the covariance of x and y divided by the product of the standard deviations of the two. That also is the same thing as the mean z product of the two variables. And that's also the same thing as the dot product between the two centered variables. Which dot product, again, basically just means you multiply together all the pairs or all the coordinates, basically, of two vectors, or you can think about it as just two lists of numbers from a variable or from two variables, and then you sum them up over the sums of squares. And the sums of squares is nothing fancy. You literally just take the squared deviation of all of the observations on one variable, and then you add them up. So it's just the numerator of the standard deviation, but it's called the sums of squares, or the sum of squares. And so that's how we come up with all these expressions here. And again, we already showed the proof. So I wanted to show you, before we try an example out together, a proof of the robustness of the correlation coefficient. So notice here that on the left-hand side, I have the relationship between days spent at a current job and year that one was born. And on the right-hand side, I've got the relationship between years spent at current job and age. And so notice here that you can write the expression for year that someone was born and the expression for their age in a way that changes the data pretty fundamentally. So let's show what that looks like here. So we can come and see, okay, so your age, let's just say your age right now. So your age right now equals 2023, right, minus the year you were born, and that's known as cohort on the GSS, right? So what that's telling us is that we can actually think about these as being transformations of one another, but it's kind of weird because we multiply one of the variables by a -1 here implicitly, and we can actually think about writing it like this to make it clearer. So it's -1 times your cohort plus the constant 2023. So that's a multiplicative change and an additive change. But notice here that the pattern of relationship between these two things is fundamentally the same. And the correlation coefficient, although it swaps sign, is exactly the same. It's 0.48. And that's because we see the same basic pattern here. So the correlation coefficient is nice and robust. Now to wrap up, I want to calculate a correlation coefficient by hand. It's generally not very efficient to do this, but it's useful to do it a few times in one's life to see how it really works. So let's say we have this set of data here to the right. I want you to find the correlation coefficient between commute and earnings. And so you can use whatever formula you want. Sometimes the computationally simpler ones have a less obvious meaning, but I think they're all the formulas I showed you have a pretty nice interpretation, and there's one that tends to work really well, which is taking the mean z product. That's what I recommend for the next homework assignment for people in 360, so let's use that one. So as a first step, we want to find the mean of each variable in order to find the z-score for each variable. So I'll let you do that now. I'm not going to show you how to do that on Stata because I'm on my iPad here, so I can show you some stuff in Notability. But you can find the mean for each data set. And then what I want you to do is check that against my work here and just kind of make sure that you're able to follow along with each step. So when you do that, what you should get is for the mean of commute, 20, and for the mean of earnings, 42. And then we can also go ahead and write into our formula n. And then our next step is to find the standard deviations. So what you'll want to do in order to do that is to get a list of the squared deviations for x. We practiced this in the last lecture. Then take the sum, right? And then take the root after you divide by n minus 1. I forgot to mention that step there in the notes, so I'll fix that in a second. But hopefully everyone remembers the standard deviation formula. So you can see here we're kind of starting to fill in the correlation coefficient formula. We could plug in 20 and 42, and we can plug in 5 minus 1 to get 4 in the denominator. So here's how we would find the standard deviation. We take all the sums of the squared deviations of x. So we take 5 minus 20, 20 minus 20, 40 minus 20, 10 minus 20, 25 minus 20. We square each one, then we add them up to get our sum of squares, just discussed, which happens to be 750. And then we take a pseudo mean, so that's 750 divided by 4, not 5, because we have to use the Bessel correction. And then finally, at the very end of all that, we can take the root, and we get 13.69. And I will let you try to do the same thing on your own for y. Let me show you that a little bit faster, though, so you may want to pause and double check that you can follow. So here, we just go ahead and we take all those deviations, we square them, we add them up. We get for our sum of squares the number 1880. Then the pseudo mean of that is 470. That's the variance. And then the root of that is 2168 for the standard deviation. So now we can fill in a whole lot more of our formula. You can see here we have basically everything but summing over all of the observations, which fortunately here is just 5 observations. So we want to get a list of the z-scores. Let's say we'll do it for x first. You could do this in 2 totally fine ways. You could take the z-score for x1, then the z-score for y1, multiply them together, and then you could do the same thing for persons 2 through 5, add them all up, divide by 4. I prefer here to just get a list of z-scores and then do the same thing for y. So our first z-score, and note by the way that this does not have a parametric meaning here. So these data don't have to be taken from a normal distribution. They can just be taken from any arbitrary distribution, and this will still have some desirable properties. So we take 5 minus 20, that's the first observation, divide by 13.69 and get negative 1.10. We do the same thing. 20 minus 20 is 0, of course, so that's just 0. 40 minus 20 divided by 13.69, that represents observation 3 is 1.46. And then we just do the same thing for the last 2 people. Then what we want to do is do the same thing for y. And you can see here, I went ahead and wrote down the answers that you should get for earnings on the right-hand side, but I am going to show you how we do it for each one here on the left-hand side. I might reverse the order of that for class. And then that gives us, in the end, a list of all of our z-scores for these 2 variables. Then we need to take the z products. So that results in this here. I was lazy, and also I figure we're usually running out of time at this point in class. So we get these z products by just simply multiplying the z-score for x and the z-score for y together. So that becomes 1.11 for the case of individual 1, 0 for individual 2, 1.21 for individual 3, and so on. And then we sum them all up, and then we take a pseudo mean. That tilde there means approximately a mean. And then we happen to get 0.295. So what that gives us is the correlation coefficient. So you can check your work by downloading the data in Stata format here, and you'll see that we get the exact same thing. I may edit in a part right here where I show that. In fact, I probably will. But in this case, since I can't immediately shift to that since I'm on the iPad, I'll just tell you that you should trust this. It's correct. You'll see it soon enough. So I want to go back really quickly and before we talk about this last bit on the geometry. So what does that mean? That tells us that the correlation between these two things is relatively large. We didn't have a huge data set, and it's rare to find really strong correlations in reality with sociological variables, so this is actually not too bad. Although it's not bad if we don't find a correlation, it just means that that's how the data are. If we plot these on a scatter plot, we've already kind of seen that once before. In fact, you could just look at the original scatter here because that gives us a good sense. Did I actually plot these? I can't remember if I did. Yeah, I probably should have shown that at some point, so I'll go back and put that into the slides, which are always linked here. But what that tells us is that we should see a moderate positive relationship on the scatter plot. I'll put that up at some point. Finally, I did briefly want to discuss one more thing here, which is one final look at correlation. This is kind of a crazy idea, but what I want to show you here is that you can also picture the geometry in a totally different way. So what we would do in this case is we would picture axis 1 as subject 1 rather than axis 1 being variable 1. And we will picture axis 2 as being subject 2. So what that means is that when we plot a particular variable, the x-coordinate is person 1's score on the variable, and the y-coordinate is person 2's score on the variable. And then we would have a second variable here. I just called it x2 to avoid confusion. And we would get the x-coordinate, here that's 5, by taking person 1's score on it, and the y-coordinate, here that's 12, by taking person 2's score on it. And we can plot that as a vector, so just a line with an arrow indicating direction. When we do that, we get something that looks a little bit like a triangle here. Note that we could actually, by finding out what quantity, when added to x2, reaches down to where x1 is, we could easily turn this into a triangle. Or we could do the same thing by thinking about adding something to x1 and getting to x2. And if you know any linear algebra, you might know that if we add to the tip of x1, x2 minus x1, so the difference vector, when we do that, we'll just get x2 back. And so we can do a little bit of fancy arithmetic. It's shown in the back. It's linear algebraic arithmetic. And what we end up getting actually is an expression for the correlation between these two variables, which is effectively the correlation formula, and that happens to be equal to the cosine of the angle between them. And it's really kind of funny when you think about it, but what ends up happening is that in the law of cosines formula, there's a component, and again, see my full lecture on this. It's kind of hard to say it super quickly. I go through it in some detail, and I think it's a better read. But basically, there's a lot of quantities in there where we have what are basically the lengths of certain vectors. And you might recall from before that I told you that the length of a vector is just it's all of its components squared and then summed, and then you take the root of the whole thing. Well, if your vectors are centered and then you take the squares and then the sum and then the root of the whole thing, that just ends up being the quantity that we call the sum of squares, or the numerator of the standard deviation. So all the lengths of these vectors are pretty much the standard deviation just multiplied by the sample size. And we can see here, when we go ahead and write out the full law of cosines, it tells us that the dot product of the two vectors, so xi minus x bar times yi minus y bar summed over I, that's the dot product. That's also the numerator of the covariance. And then if we divide the whole thing by the product of the sum of squares for each variable, if we then put n minus 1 in the denominator of the numerator and the denominator of the denominator, that happens to give us exactly the covariance over the standard deviation of x times the standard deviation of y, which is the correlation formula, but that's also the formula that gives us the equation for the cosine of theta, where theta is the angle between two vectors. So you can see here that the angle between these two vectors is relatively small, which means that the vectors are pointing in close to the same direction. And what that means is that these two variables actually have a close relationship in this case. Now, if you actually try to compute the correlation by hand here, you'll run into problems because the sample correlation formula isn't well defined when you've got only 2 observations per variable. The idea is that you can generalize this, and it actually works in 3 dimensions, although 3 dimensions is just slightly less intuitive. And then it works in 4 and 5 dimensions, although we know that those are pretty hard to picture. But the idea is that basically using the law of cosines and generalizing it, again, go see my full video on that if you are interested in this, tells us that the correlation formula in the expression that we saw before, so the dot product of the deviation vectors over the sum of squares, or in other words, the length of one vector times the sum of squares for y, or the length of that other vector, actually also gives us the correlation it is the correlation formula, but it's also the cosine of the angle between the 2 vectors. So if you picture each of the variables here, again, not as axes, but as vectors in the space, the angular closeness of the vectors, or a simple transformation of it, the cosine, is another way of seeing how closely related the 2 variables are. So here's the executive summary again for good measure. I'm not going to step through this, but I just wanted to put it up here for your reference. And notice also that we can now go ahead and summarize our measures of association pretty nicely. I'm actually going to update this slightly, so see the slides, because I realized that I wanted to change this a little bit from last semester. I forgot about this slide, to be honest. And then I finally wanted to note that we actually went through most of the optional material this time in the course of the lecture. You can take a look at this if you want. Here I prove the law of cosines and give a link to the video, and then I show how that applies to our situation here. But you don't need to know that necessarily for this class, but I think it's a very cool and kind of beautiful alternative picture on the geometry. So go see that full lecture if you're interested. Thanks everyone for watching, and I hope you stick with the course.